Okay. Hi, everyone. Thanks for coming to another q-matroids seminar. Today we have Relinde Jurrius from the Netherlands Defense Academy, who's going to be talking about direct sum of q-matroids. Go ahead, Relinde.
Thanks, Sheila, and thanks for inviting me to speak in this seminar. So I'm going to talk to you about the direct sum of some generalization, one can say, of matroids. And now usually the direct sum is like an easy construction to get new things out of olds, but it turns out that for q-matroids it's not that straightforward. So I will spend a lot of time in this talk to first give you a bit of a feeling on what a q-matroid is, and also on why it is difficult to get the direct sum and why some of the obvious definitions fail. But I will also tell you the conclusion, or well, the solution I came up with together with Michaela Celia. So yes, so I will first, of course, the first word here had to be matroids, as we'll come back a few more times, I guess. I will give you a way of viewing matroids that makes the Q analog a bit more logical, I think. And then I will talk about like a first try for the direct sum, and then we explain how this can be done via adding loops and using matroid union. So first, for an alternate view of matroids, I actually learned about that from Henry Crepo. Here he is in Waterloo, the last like physical matroid meeting I think we had, and he actually developed this already in his PhD thesis, and I think, well, it sort of slumbered for a while and people didn't realize that it existed, but now it turns out to be useful again. Actually, he defined already q-matroids, and he didn't call them like that, but he did study them. So I'm going to give you a view of a matroid that is a coloring of a lattice. So the picture you see here with all the colors, it's the subspace lattice of the set of 4 points. So I have 4 elements, A, B, C, D, and I'm just going to take all the subsets, and I'm going to draw a line between them if one is directly covered by another. And now I'm going to color all these lines in a way that the red means the rank goes up, and the green means the line stays, the rank stays the same. And this gives you like the full rank function of a matroid. So the lattice I drew here, it's actually the matroid of which you see the picture. You can see that all the points are independent. So starting from the empty set, the rank goes up. All the points have rank 1. And then we see that, for example, BC, which is a double point, they are parallel elements. So there the rank doesn't go up if I go from B to BC and if I go from C to CD. So that's a green line. But then if I would add to BC, for example, the point D, then I see that I go up in rank again. I get something of rank 2. And then if I add the final element, if I add A, I get to rank 3. And so in this way, it sort of encapsulates the whole rank function of the matroid. And actually all other things you want to know about matroids, you can find them in this coloring. For example, if you want to know what are the independent sets, well, the independent sets are just the sets where everything below it is red. And so, for example, CD is an independent set because, well, the 2 lines here and then the lines going further down, they are all red. And ABCD, it's independent because, well, there's a lot of lines that go down, but every route that I take going down, it's always completely red. Another thing you can find quite easily in this way of viewing it is, for example, the closure. Because what do we do if we take a closure of a set? Well, we add as many points as possible without the rank going up. So that means that you start in a set. For example, I wanted to find the closure of B. And what am I going to do? I'm going to add things such that the rank doesn't go up. So that means I have to try to go up with a green line. So I can go to BC. And then here there are no green lines to go up anymore. Both going out are red. So that means BC is a closed set. It's a flat. I can't add anything more. So this whole thing with coloring the lattice, it lets you get back all important properties of matroids. And actually, you can completely axiomatize matroids by using this kind of coloring. Because what can you do? You can say, well, something is a matroid if I start with this subset lattice, the Boolean lattice, and then I'm going to color it. And every interval of height 2, so every diamond, is one of these 4. So it can either be all red, so that's like something of rank 2. It can be all green, so we basically have 2 loops in the middle. It can be mixed, so something of rank going up by 1 and another stays the same. Or you can have a prime, so you have 2 things taking the rank up, but if you take the union of that, the rank stays the same. Now, and this actually completely defines the rank function of a matroid. You can see that by sort of checking that, well, this rank function is going to be well defined. If every diamond looks like this, then all the chains between 0 and an element will have the same number of red elements, of red lines, which of course is needed if you want your rank function to be well defined. And also it's going to be an increasing function. And the semi-modularity is actually covered by the fact that if you would take this prime diamond and you flip it upside down, so the green below and the red on top, that's never appearing, because that would be 2 loops that sum to something of rank 1. And so with all the other options you have here. So given that we have this view of matroids with coloring the lattice, it makes hopefully a bit more sense to take a following sort of generalization of this idea. And that's a Q analog. And what you do in a Q analog is, instead of looking at the Boolean lattice, so sets and subsets, you're going to look at the subspace lattice. So that means you take a subspace of finite dimension. I take it over a finite field to make everything manageable, but strictly speaking, you can take any field. And then we can sort of translate between these 2 lattices. So the atoms in the Boolean lattice, they are the elements, right? The things on the first thing above 0. For the subspace lattice, these are the one-dimensional subspaces. If you count the height of an element, then it's the size for the Boolean lattice and the dimension for the subspace lattice. We can count how many atoms there are. So there are n, the number of elements in the set for the Boolean lattice, and the number of one-dimensional subspace is q to the n minus 1 over q minus 1, which is like the Q analog of a natural number. And the intersection in both lattices gives the role of the meet in the lattice, and the join is for the Boolean lattice, the union, and for the subspace lattice, it's the vector space sum. And actually you can go back from your Q analog to like a classical case by letting Q go to 1. So if you like, is set theory is just projective geometry over the field with 1 element. So this means that this whole business with coloring the Boolean lattice in a certain way that it gives you back a matroid, I can do a similar thing on a subspace lattice. And then it will look, for example, like this. So here you have a 3-dimensional space over F2. You see all the one-dimensional spaces, and I wrote down the vectors that generate these one-dimensional spaces. You have the 2-dimensional spaces. There are 7 one-dimensional spaces, 7 2-dimensional spaces. This is actually the Fano plane, of course. And you can do the same kind of coloring, right? So you can say, well, the 0 space, it has rank 0. And now, for example, the space spanned by 0, 1, 0, it has rank 1. And then the space that is spanned by 1, 0, 0, 0, 1, 0, the one over here, it also has rank 1. And actually the whole, this whole matroid has rank 1. And you see that all the one-dimensional spaces have rank 1 except for one over here, that's a loop. And also here, well, you can see the same thing for independence and closure and stuff like that. And you can also axiomatize what kind of, well, diamonds will occur. And the diamonds will look even more like diamonds than before, because you will look at all the intervals of height 2. And so now they don't have just 2 elements in between, but they have q+1 in between, if it's over a finite field. And it turns out that again, you have only 4 possibilities that are allowed if you want to make this, well, a q-matroid. You can make everything red, you can make everything green, you can make the bottom part red and the upper part green. And then you have a mixed variant, and there's actually only one thing allowed, and that's saying I have 1 loop, and the rest is all of rank 1. And that's because, well, we want our rank function to be semi-modular. So that means that if I have 2 loops, the rank of this, the sum of this can never have rank 1. So as soon as I have 2 green ones down here, I'm in the case of the 0 diamond. So the only possibility for a mixed diamond is that almost everything is red and only one of them is green. And well, some of these you can actually find in the picture I just showed, right? So for example, between 1, 1, 1 and the top, you see that there is a green diamond. So there are 3 spaces in between, this one and that one and that one. And then you go up to E and everything is green. You don't have the all red diamond here because the thing has only rank 1. But you can see, for example, between 1, 0, 0 and the top, you can see a prime. So only reds on the first level and then only greens going up. And you can see a mixed one between 0 and the space here at the left. So this is the idea of a q-matroid. We start with a subspace lattice and we're going to color it. And we do that in a way that only those 4 diamonds are allowed to occur. And it turns out that it has a lot of other, I mean, we can also speak about independent spaces and closure and flats and things like that by just directly generalizing it from the way that I just explained. Okay, so these q-matroids became in fashion again a few years ago. And so the question is still, you know, what results on matroids can we find a q analog of? And so we wanted to see what can we do with the direct sum. And well, for a first try, I will explain a bit, you know, how you would make a direct sum for matroids and why that doesn't work for q-matroids. So our first try was, well, what is actually the definition of the direct sum for matroids? Well, there are, of course, like 100 equivalent definitions, but some of them sounded most promising. One is to say that if I take 2 matroids, M1 and M2, and I define them via their rank function, then the direct sum is going to be the disjoint union of the ground sets. And then if I take something in this union, I'm going to define its rank by intersecting it with E1 and intersecting it with E2. And oh, there is actually a 1 missing over here. So I take the rank of the part that is in E1 in the matroid M1, and I take the part that is in E2, and I take the rank in the matroid M2. And this is actually equivalent to saying, well, what am I going to do for my direct sum? I'm going to start with my two matroids, and I take as a ground set the disjoint union. And now I'm going to say, well, if I'm going to restrict my direct sum to either E2 or E1, I'm going to end up with, well, exactly that matroid. So if I restrict to E1, I get back M1. And if I restrict to E2, I get back M2. And also if I contract, like if I contract E2, then I get also back M1. So if I delete everything that has something to, well, if I ignore everything that has something to do with E2, I just get M1. And the same thing for if I contract E1, I get back M2. So for the Q analog, we were wondering if we could do something like that. Well, if you take the first definition, then you run into a very important problem that you have in the Q analog, and that's the following. So for sets, if you have a disjoint union of two smaller sets, then if I have something in the big set, I can always decompose it as a disjoint union of something in the first and something in the second set. Right? I mean, if I just glue two sets together and I take a subset, it's always like a disjoint union of something in E1 and something in E2. But this is not true for vector spaces. And well, I can show it with an example. So suppose I take E1, which is a vector space spanned by, well, the first two unit vectors, and I take E2, which is spanned by the third one. And if I add them together, I get the full three-dimensional vector space. But now if I look, for example, at the one-dimensional space that is spanned by 1, 1, 1, well, it has trivial intersection, both with E1 and E2. So I can't write it as the sum of something in E1 plus the sum of something in E2. And this whole decomposing argument, it doesn't work. Or you can also flip it the other way around and say, well, if I'm going to take the vector space sum, then some of the elements, like in the big space, are going to be of the sum, well, of the form, it's a direct sum of something in E1 and something in E2. But most of the spaces are, well, not of that form, and we have to do something with them, right? If I go back to this this rank definition, I mean, I just had an example where these intersections were both 0. So that would mean that no matter what my matroid M1 and M2 was going to be, this A was always going to be a loop. Well, that's of course not going to work if you do a definition like that. So we sort of have to come up with something of all these spaces that aren't a direct sum of something in E1 and in E2. And so our naive attempt was, well, what do we want? We want that this minor property holds, right? So that there is a restriction and a contraction, and you get 2 times M1 and 2 times M2. And we sort of take this as a definition and hope that the rank axioms will take care of the rest. And they do take care of some things, right? So, and I will show that by example. So here's an attempt to make the sum of a one-dimensional space and a prime diamond. So what do we have? This 1, 0, 0 over here. It's a red space, so it's U11. And then I have U12, which is like the interval between 1, 0, 0 and E. On the other hand, I have that the interval between 0 and the space in the middle here is also U12. And then on top of that, I glue a copy of U11. So what do? Is you take your full space, you take a copy of M1 and one of M2, and then you put M2 on top of M1 and M1 on top of M2. So you have like these 4 minors, you want to put them in this way. And then you sort of hope that you can juggle around a bit and see if we can color the rest of them. Well, in this case, that's going to work. So for example, what we can say is this space over here, there's some gray lines going down, but we know that this matroid is going to have rank 2, right? Because we can go like red, red, green. So the whole thing has rank 2. So that means that if I go from 0 to here to something gray and then with something green, it means that my gray thing actually had to be red because I need to encounter 2 reds if I go to the top. And a similar one over here, and here are also some. So this gray one I can also color. You can also say something about like everything that covers 0, because you can prove also by semi-modularity, that the only loops that will appear are loops that come from either M1 or M2. And since both of them didn't have loops, the whole bottom here has to be red. And you get something similar dually that says that if you have anything red on top, it also has to come like in a complete interval. So if I make this thing is red, and if another one is red, then the whole interval that contains these two, so the meat of them is over here, everything going up should have been red, but it's not because I already have the green over here. So that means that I can't have anything more red on top, on the lowest level than this one, and so the other ones are going to be green. Well, and then I know everything that's on the upper level and everything on the lowest level, and the thing in between, I can just color them because I know the total rank is 2. So it turns out that, you know, jiggling around with semi-modularity and saying, well, I want my minors to be in the right position, is going to actually define the direct sum for us. So hooray, and we tried to prove for a while that this will always work. But of course, this example is way too small to actually give us enough intuition. So at some point we decided to make something bigger. And I'm not going to make a picture for you because the thing is too big, which is, you know, one of the disadvantages of q-matroids. You know, things blow up like quite soon. So we're going to make the sum of U12 and U12. So that's 2 copies of a prime diamond. So all red and then all green on top of that. And so the total rank of this thing is 2. There are no loops because there are no loops in the matroids we started with. And so that means we know everything that's going on dimension 1. And so that means that in order to completely determine this matroid, it's enough to say for every 2-dimensional space, if it's a basis or if it's a circuit. And well, there are 2 circuits to start with, which are like the matroids you started with. And these 2 things can be extended to what geometers call a spread. And that means there are 5 trivially intersecting 2 spaces, and every 1-dimensional space is in exactly one of the spread elements. So, and there's actually equivalent ways of doing that, but you can look at this whole spread. You can prove that all other 2 spaces are bases, but in this spread, we know 2 of the elements are circuits, and for the other 3, semi-modularity is not helping you. So the rank axioms don't decide what they have to be, if they have to be circuits or bases. So you can basically choose. So that means that the sum in the definition that we just had is not uniquely defined, because we have this spread and we know 2 of those elements are circuits. And we can choose to have these be the only circuits, but we can also have 3 or 4 or 5 circuits. And so they all satisfy this condition that the minors are M1 and M2, but they are really different q-matroids. So so that was annoying. So our naive attempt didn't really work. So the goal is to find some other equivalent description of the direct sum that actually does allow for a Q analog. And we found that by sort of taking a detour by explaining what is the direct sum as a combination of adding loops and then using matroid union. And I will first explain how that works in the classical case. Well, let me first tell you what matroid union is, except for a nice blog. The union of 2 matroids is a matroid on a ground set that is, well, the union of the 2 ground sets. They don't necessarily have to be disjoint. And the independent sets are just all the joints of independent sets where one is in the first matroid and the other is in the second. Well, I write it in terms of independence. And this is actually the first time independence comes up, because it's actually not a very useful thing to do for q-matroids, but I think it's a very nice definition for a matroid union in the classical case, because you can also look at its rank function, and let's be honest, it looks slightly terrible, because you have to take a minimum over a lot of spaces of the sum of the ranks in M1 and in M2 of, and then some size of, well, everything that's in A but not in X. So it's not a very convenient thing. If you look at the rank function, it's not very intuitive. But what you can see already is that if E1 and E2 were disjoint, then this independent set definition is exactly the independent definition for the direct sum for classical matroids, right? Because then you just also take the sum of, you know, something in the first and something in the second. Unfortunately, if you would take a direct Q analog of this, things would go south, because then you would only have independent spaces that are the sum of something in E1 and something in E2. And we already know that there are a lot of other spaces that can't be written in that form. And it would then mean that they can't be independent. And well, that sounds very fishy, and that's not going to give you a valid Q-matroid. Now, what do we do with this matroid union? Well, we can write a direct sum in a slightly more involved way. So we're going to start with two matroids on disjoint ground sets, and we say E is the disjoint union of these ground sets. And now I'm going to make a matroid that I call M1 prime. And what do? I'm actually going to add loops to M1 that are in the spots of M2. So to say. So it means I get a matroid that if I restrict it to E1, I just get my first matroid back. And if I restrict it to E2, then I get only loops. And I do this also the other way around for M2. So I get a matroid M2 prime, and it's a matroid also on the big set, such that if I restrict to E2, I get back M2. And if I restrict to E1, I get only loops. I get something of rank 0. And now the direct sum of M1 and M2 is the same thing as the matroid union of this M1 prime and M2 prime. And you can see that from this independence definition, because, well, what are the independent spaces in M1 prime and M2 prime? Well, since I was adding only loops, the independent spaces are exactly the independent spaces of M1 and the independent spaces of M2, and you just get the regular definition back. But the good thing is that this definition is actually going to allow us for a Q analog, because now there are two things that we have to do. We have to add loops, which, well, it sounds a bit like a contradiction because we don't know how to, you know, take a direct sum. That was the whole goal. But adding loops turns out to be so easy that we can do that. And the second step is to take the matroid union, but we can define matroid union on two ground spaces that are actually the same space. So this whole problem with I can't write all my spaces as the sum of something in the first and something in the other, it disappears in matroid union. So even though, like, from in classical matroids, it sounds like a rather elaborate way to do something as easy as the direct sum, it actually is a way that allows us to take a Q analog of it. And so I will tell you some of the technical stuff that we had to do in order to do that. I will sort of skip over all the proofs because they are, well, quite long and annoying, but I wanted to convey sort of the idea of what we have here. So first, let's see how matroid union for q-matroids work. And the good thing is that Benjamin Janey and Heide Gluing-Luersen already worked on the Q analog of polymatroids. Even though the word polymatroid is not here, someone who uses polymatroids will recognize it. So we take a function f that is actually the rank function of a polymatroid, which means it's a function that's non-negative and it's integer valued and it's increasing and it's submodular. So it's almost a matroid, but not completely, which is why it's a polymatroid. And also if we put 0 on it, you get back 0. And then if you take this function and you add the dimension, so for any A in your ground space, you can make a matroid out of it by taking the following rank function. You take this polymatroid function, you add the dimension of A and then minus the dimension of A intersected with X, where you let X run over every possible subspace. actually you only have to take the ones that are contained in A, because otherwise this quantity will become too big anyway. But you have to take some minimum. And you have to work a bit to show that this is a rank function. You have to see that it satisfies all rank axioms. Luckily, this was already done in the literature for classical matroids, so we could, well, I mean, it was already done, but we independently did the same thing with Michaela. And you can just, you know, take your favorite one that exists and take a Q analog of it, and it's sort of okay-ish. And once you have that, you have to apply it in order to get a matroid union. And what you can do is you can say, well, I take my function f to be the rank of A in the first matroid plus the rank of A in the second matroid. And if I put that quantity over here inside your minimum, of course, if I prove that f is a non-negative integer valued increasing submodular function where the f of 0 is 0, well, basically if it satisfies everything in the first theorem, then you can show that you get a matroid again, and that's how we define the matroid union. So the matroid union is a combination of these two things. We learned something about Q polymatroids on the way, and if we take a certain Q polymatroid that is like a combination of two others, we get the definition of matroid union for Q matroids. So that was nice. It's not a very manageable definition. So we
May
also
I ask?
Sorry, yes.
Relinde, may I ask? So R1 of A, so I assume here R1 is, so to speak, the rank function of your M1 prime after you have embedded it with the added loop space into M.
Yes. Yes, you're right. I didn't write that down in a good way, but it is, yeah.
Yeah, thank you. Sure.
Yeah. Yeah, so I'm actually not doing things in the right order here. Well, that's not completely true. So this holds in general, but if you are on the same ground space. So there's two things you can do. You can either take your rank 1 and rank 2 to be in this M1 prime and M2 prime, or this theorem holds if M1 and M2 have the same ground space. So sorry, this is not very clear in my slides. I realize now that I messed up the order. I will do a quick recap later on for this. But the conclusion is that we can talk about matroid union of Q matroids, and we can do it in terms of the rank function, and it looks, well, it's not a very manageable thing with this whole minimum going on, but it works. Actually, we also know something about the independent spaces, but it doesn't become more manageable because the independent spaces, you also have to demand not just that it is the sum of two independent spaces of the smaller matroids, but also that all their subspaces are of that form. And so you keep having the problem of defining something by running over all subspaces. Okay, so the other part that we had to do is adding a loop. And now, of course, that's just a direct sum of a matroid with a U01. And strictly speaking, we want to define the direct sum, but the thing for adding loops is that it's relatively easy because there's not too many spaces sort of left after you have asked for these minors to be in the right place, right? Because what you want to do is you want to say, well, I can add a loop, then I get something that I call M prime. It has as a ground space, E plus the loop, which should actually be a direct sum. And now if I take something in this bigger space, then I can always write it in this way. And that's a bit strange at first. So what you can do is you can add a loop to it. And then you can say, well, everything that contains a loop can be written in a unique way as something that was in my small matroid, direct sum with the loop. And now we say that the rank function of my matroid with the loop added is going to be the same as the rank function as that I had, but for this other thing. So you can sort of see this as a projection. It's not quite a projection, but it will work like that. Now, of course, if I take something that was already in my first matroid to begin with, then the rank is just going to be the rank that it already was, right? On the other hand, if something contains the loop, then I can just intersect it with the smaller ground space I started with, and I take the rank over there. And now there are some spaces left that are not contained in E and that also don't contain the loop, but they are sort of close enough to either something that contains a loop or E. Because if I have such a space, and that's my A prime here, it's always in between something that contains the loop, because I can just add the loop to it. And if I intersect it with my space E, I get something that's inside E. And there's also my space that is like the projection of that is also contained in E. So the thing is that what we have now is that my space, of which I don't know yet the rank, it's contained in a diamond where all other three things I know what is the rank. And then semi-modularity will help me out, or well, actually not just semi-modularity, but this coloring things will help me determine what the rank is. So that means I can add a loop to a q-matroid. And if I do this multiple times, I can add like a whole space of loops. So, well, this was maybe a bit fast, but it is what you can do technically. So back to the hand waving part, is this the summary for how to construct the direct sum of two q-matroids? Well, first we're going to say, well, the new ground space is going to be the direct sum of E1 and E2. We have to make sure that they don't intersect, or that they intersect trivially. And actually, we also want that one is the orthogonal complement of the other. And we need that later on for duality. I didn't talk too much about duality, but I'll say a bit about that later. And then we're going to add loops to both our matroids to make them of the same dimension. So M1 prime is going to be a q-matroid such that if I restrict it to E1, I get back M1, so I get the right minor. And if I restrict it to E2, I just get loops. I only get green covers. And I do the same thing for M2. I make a matroid M2 prime. And if I restrict it to E2, I get back M2. And if I restrict it to E1, it contains only loops. So you get something similar as before. And so you have you have two matroids, and one of them has like your interesting part on the place of E1 and zeros on the other matroid, and it's the other way around if you look at E2. And then of course my M1 prime and M2 prime, they contain a lot more spaces than just these two restrictions, but we don't really care about that. We let them float around, and they're actually going to be helpful because now what we can do is we can define the direct sum as the matroid union of this M1 prime and M2 prime. And that actually gives us something that's defined uniquely, well, up to isomorphism. There are some coordinate choices involved, but at least now you don't get your problem anymore with one definition that gives you several like different matroids. Well, the question is, of course, is this the only way to do it? Is it the best way to do it? We don't know. As a bit of motivation, we did prove some theorems about it. One is that the dual of the direct sum is the direct sum of the duals, which I think is a nice property to have. By the way, duality in your colored lattice works like flipping your lattice upside down and changing all red in green and the other way around. And actually, so if you know that, then we use that result to prove that these minors occur in the right place. The restriction is sort of easy to see, and the contraction is quite difficult. But if you already have the duality result, then the restriction becomes the contraction, and it follows. So this thing that we started out as our naive definition in the beginning, it has this property, our definition. So we think that these are some suggestions that this might be a nice thought out definition. Of course, there are some more questions to ask. And well, I just have two of them now, which I think are important to look at. And one is to say, how does this work on representable q-matroids? Well, I won't completely define what it is, but you can guess that it has something to do with there's a matrix attached to it. And one would say that, well, the direct sum of representable matroids, I know how that works. I take my matrix and then they do zeros and zeros and then they do the other matrix. Unfortunately, that doesn't work. So we tried that for the Q analog and you get something that's not well defined. It sort of depends on how you pick your coordinates in the matrix. And so you can pick like different representations of the same matroid, do the sum in that way and get inequivalent answers. So there is something specifically going on there and I don't know what, but I would be very interested in finding out. And the second thing is, if you talk about direct sum, you would also like to talk about, well, sort of the inverse operation, which is talking about which matroids are connected and which not. And we tried this. I mean, we sort of tried this direct sum from two approaches and hoped that something fell out. Well, the direct sum definition was the first that fell out because for connectedness, we still have no idea. So in the classical case, you have an equivalence relation on all the points that says 2 points are equivalent if they are contained in a circuit. And then you can prove that this is an equivalence relation. And the problem is, if you take the Q analog of that, so you say, well, I take one-dimensional spaces and they are equivalent if they are contained in a circuit. That's not an equivalence relation. Like your counterexample are already in dimension 3. So that's not going to work. So you have to come up with something else. We did come up with something else that didn't consider circuits, but considered, well, co-circuits and their duals hyperplanes. But then we ended up with something that didn't behave nicely under duality. And one of the problems we think it's related to that in normal matroids, you have that the circuit and the co-circuit can never intersect in a single element. And the Q analog of this is false. So a circuit and a co-circuit in a Q matroid can intersect in dimension 1. And all the places where our connectedness goes wrong is exactly where this intersection in dimension 1 occurs. So we think it has something to do with that, but again, conjectures, question marks, we don't know. So if you have any idea about this, or if you would like to have an idea about this, tell us, because we are, well, Michaela and I at least are eager to talk about that. And well, this is what I wanted to say. So I want to thank you for your attention, and all the details are in the paper online.
Thank you so much, Relinde. Let's do a round of applause. So if everyone can please unmute, and then I'll count to 3 and then we'll clap. 1, 2, 3. And does anyone have any questions or conjectures?
I've got a question. Are your direct sums, does that preserve representability?
Well, we don't know. I think so, but well, yeah, no, I don't know, because I wouldn't know how to get from the representation of 2 Q matroids to the representation of the direct sum. Like the logical thing of, you know, just gluing the matrices together doesn't work. So you have to be careful in a way to pick your representations in order to make them compatible. And I have no idea.
Hey, that was also the question on my mind. You were explaining this with a block diagonal, and that you get many different non-equivalent matroids that way, q-matroids. But do you have a feeling of whether there would be one of those that may be actually your direct sum? Or do you know it's not the case? Have you run examples?
Well, no, we didn't run too much examples. I mean, we run an example and we ended up with a counterexample more or less by accident. Because what we did was this example where we did u12 plus u12. So you get something 4-dimensional. We tried to represent it, and for some reason we came up with all these different things for 2, 3, and 4, and 5 circuits. It actually gave us one that isn't representable. But
is one of them the direct sum, as you explain later what the direct sum is? One of them is, right?
Yeah. So one of them is, and the question is, if we would have stared at, you know, our separate representations in the beginning, could we sort of argue why that were the right representations?
Yeah, exactly. That is my question. So can one single it out?
Yeah, I don't know, because from an algebraic point of view, these things are really the same. Like, because what you do is you represent them over F8, and what you do is you basically need a 1/2 matrix, and you do 1 and then some other element in F8 that's non-zero. And like from an algebraic perspective, I don't think it matters which one of those things I should pick. Like,
no, I think it matters immediately. If you look at the rank, how you define the rank function, G times your column, your matrix whose column space is the given space, then you see immediately that there is interaction between G1 and G2 from the 2 blocks, and therefore also algebraically it matters. But how to single out which one could be the good choice, that was my question.
No, so I also don't know, and I think that a way to start would be to see how maybe if someone already found some notion of direct sum for in coding theory, but I also didn't really see that. I mean, there is of course you can do concatenation, but that sort of doesn't feel like the right thing. And so I was hoping that someone in I was hoping that in coding theory there were some results that would be helpful, but I didn't find them yet. I have to say I didn't look very closely lately, so there might be something around. But I would start looking at if someone in coding theory did something that could help for that.
I just ask your direct sum comes by combining these 2 results, and do either one of those results behave nicely, like from an intuitive way with respect to representation?
Well, adding loops does, because it's just adding 0 columns. So we did manage to prove that, and we tried. Doing the direct sum, because there are some results in the classical case on what you have to do. Because if you take matroid union in the classical case, then you just take your 2 representations, and the lower one you have to multiply it by some transcendental element, and then you just prove that all the submatrices have the right determinant or something like that. But in the Q analog, that's not going to work exactly for the same reason, because you can have subspaces that are not like neatly spanned by columns. So I don't know for matroid union how representability works. And like the obvious method is not true. And in a sense, the direct sum is an easier thing to do than matroid union. I mean, if you want to do the full generation for matroid union, that might be too difficult. So one approach could be indeed to try and see how representability behaves under matroid union, but that could also be like too big of a gun to tackle the problem. I don't know if that's a saying in English, but
if you say that circuits don't cross a partition. There's all these different ways you could write down the matroids disconnected with these two components. Have you looked at all of them? Do any of them kind of make sense for what you're doing, or are they all different, or they all fail?
Yeah, so what you can do, so we did look at that. So at first we thought, well, maybe it's just that it's not defined up to isomorphism, because what you do is you start with these two minors, and of course, as long as you take two-dimensional spaces that don't intersect, you have a lot of freedom how to choose them. But the thing is, no matter how you choose them, all the two spaces that intersect with one of these two spaces is going to be independent by semi-modularity. And then you end up, I think, with 6 subspaces that don't intersect. And they give like 2 ways to make a spread. So you have the 2 things you started with, and then either 3 of them or the other 3 of them. And so that means that basically one set of 3, you have to make them independent anyway, and then you can, for the other 3, you have to decide if they are circuits or not. And this is really up to, so you really get a different number of circuits of dimension 2, so you really get a different q-matroid, and it doesn't depend on your coordinatization of the circuit. So we know that there's really 4 different options independent of coordinatization.
What if you started with a q-matroid that doesn't decompose as a direct sum, and then you pick an element? Do you know that the deletion or the contraction of that element doesn't decompose as a direct sum?
That's a very good question, because we don't know when a q-matroid decomposes as a direct sum.
Okay.
Well, I mean, we do
sure.
like from this point of view, but if you want to reverse the process, you have to reverse matroid union, which is already a difficult thing in the classical case. So I didn't really want to get caught up in that for the Q analog of things.
Yeah.
So the problem is I don't know how to decompose.
Okay. I'm trying to find backdoor ways to get at connectivity.
Yeah. So I would like such a backdoor, but up until now I didn't really see how this thing would work. We had some intuitive ideas actually of how decomposition should work, and it doesn't comply with the definition of direct sum that we found. So there are really strange things going on. So I wouldn't be surprised if there is a definition for connectivity that doesn't play nice with this definition of direct sum.
Okay.
That wouldn't be a nice way to view the world, but I also wouldn't be surprised about it.
Thank you, Relinde.
Okay, maybe I'll stop the recording there and we can